Okay, it is our last day of class. Uh, and what I've done is I've posed some problems here and probed what people in the class do with them, and I see that there are things people need to kind of refresh themselves on. Now, first problem, everybody got that one. You have 7x minus 3 equals 12. You add 3 to both sides. And you get 7x equals 15. And then you divide both sides by 7. 7 divided by 7 is 1. You get x equals 15 sevenths. And then you could check. It's a good idea to check. So if you put this number back in here for x, you get 7 multiplied by 15 over 7 minus 3 equals 12. Well, now when you multiply fractions, you multiply numerators and multiply denominators. So this 7 times 15 over 7 could really be written 7 over 1 times 15 over 7 minus 3 equals 12. And furthermore, you're going to multiply denominators, you're going to multiply numerators if you work this out. But we could multiply the denominators in a different order. And 7 over 7, 7 times 1. 7 over 7 is just 1. Okay. And I do this because of mistakes that I saw previously. First of all, if you're multiplying fractions, you want to write it as 7 over 1. And then you got this product, and you've got a 7 in the numerator here and a 7 in the denominator here, and you can cancel. Okay, that's the easy way to do it, but this is why it works. And if you don't see that this is 7 over 1, so this 7's in the numerator and this 7's in the denominator, you're not going to see that. So I recommend at least you do this, and then if you want to cancel the 7's, okay. But you have to understand the rules for cancellation. All right. So, and I'm going to go over these very quickly. Okay, so you can refer back to this, get my words of wisdom, laugh at my mistakes, whatever it takes. Okay. Now, second problem, and I pretty much got this. When I had to give a hint to some people, I said, you know, I don't know what to do with this. Well, use the distributive law. That's all I said. And everybody got it. Okay. So you have to know that's the instance of the distributive law. So you got 2 times the quantity 5x minus 4. It's 3 times the quantity 6x plus 7. Okay, you multiply by 2. It's 2 times 5x minus 2 times 4. It's 3 times 6x plus 3 times 7. And then what's 2 times 5x? Well, that's 10x. That's 8. This is 18x. And this is 21. And you do the steps that everybody knows how to do it. Okay. You subtract 18 from both sides. You add 8 to both sides. And you get negative 8x equals 29. You divide both sides by negative 8. And you get x equals negative 29 over 8. Okay. And excuse me a minute. I don't know what's the matter with this camera. It just somehow decides to zoom back. Okay, well, it did. Okay, so that's pretty straightforward. I'm going to skip down the most obvious of the remaining problems would have x plus 2 times x minus 4 equals 0. By inspection, x equals -2 or x equals 4 is a solution. If x equals -2, you got -2 plus 2, which is 0, which multiplied by whatever this turns out to be. Easy to figure it out, but you don't have to. You know that whatever this is, x equals -2 is going to give you 0. Because this is 0. When you multiply something by 0, you get 0. And if x equals 4, this is 0. So once multiplied by whatever this is, you're going to get 0. Okay. Now, the other way, we break this down, and we have x plus 2 times x minus 4 equals 0. And we use that fact break this into two equations. And my advice when we did this was always write this or, because this would make it 0. If this is true, the whole thing is 0. If this is true, the whole thing is 0. We want that logic. And if you're not writing that logic, you're going to forget what to do. You're going to be likely to forget what to do, which a lot of people here did. Okay. People look at this, even though we've done it recently and didn't do it. And I think you really need to write these things out the way I'm telling you to, because writing them out with your hands is the best way that I can think of for most people to reinforce what they're doing so that they remember it later. Also doing a lot of problems. And I've provided a fairly large problem set, at least up through midterm, with some solutions or some answers at least. So, you know, find time, use that. Anyhow, you solve this equation. I'll just put 3 dots down here because we know how to solve. We're going to subtract 2 from both sides. We're going to get x equals -2 or x equals 4. So that the solution set could be written as a set -2, 4. Okay. Now review that. We've done that. We did that in detail. We spent a good bit of time on it. So you can go back and notes, whatever it takes. That's a no-brainer that you ought to be able to do, that you will need to be able to do this. Okay. And probably not for an easy problem like this, probably for one like the next one, which is also easy if you just know the logic. Okay. And the logic is, let's see, okay, where is the board all the way over here? It's still not there. No, sure. Okay. Okay, so we have the equation 2x minus 3 multiplied by 3x plus 4 equals 0. We could try inspection, but you're probably not going to see what the solutions are until you split this into 2 equations. The logic is identical to what I did down here, which is identical to what I did up here, but this is the form we want to write it in. 2x minus 3 equals 0. Big capital or 3x plus 4 equals 0. Okay. Now, make sure that's visible. Just barely. Move it over just a little more like this. Okay. Okay, so we can solve this equation. 2x minus 3 plus 3 equals 0 plus 3. Change it 2x equals 3. 2x over 2 equals 3 over 2. X equals 3 halves. Write out every step because A lot of people are simply not retaining what they've learned to do because they're skipping steps and stuff. Okay. And then we got not enough room here. I'll write my or. I'm going to have to borrow a little space for this area. Got a little bit of board space and try to use it all. Sometimes that's not a good idea. You get 3x plus 4 minus 4 equals 0 minus 4. And this is very straightforward. You get 3x equals negative 4. 3x divided by 3 equals negative 4 divided by 3. X equals negative 4. Your solution set is negative 4/3, 3/2. Now, in every case, it should be an automatic part of the process when you solve a problem that you check. Again, what I did here is the same thing I did here, just representing the fact that this could be 0 or this could be 0. That's exactly what we've done. Okay. Now, we have another equation. 3 times the absolute value of 2x minus 4 equals 6. Now, this is going to end up splitting in a way kind of similar, but for a different reason, similar to what we do here. First, we divide by 3. And that gives us absolute value of 2x minus 4 equals 2. Now, the absolute value is equal to 2x minus 4. Well, let's put it this way. We understand absolute value, like the absolute value of 10 is 10. The absolute value of negative 14 is 14. Okay? If the thing inside the absolute value sign is negative, then you're going to end up with something of the opposite sign. Now, the whole point then is that if the absolute value of something is 2, what's that something? What has an absolute value of 2? Well, it's either 2 or negative 2. So we get 2 equations out of this. 2x plus, so minus 4 is equal to, or 2x minus 4 would equal negative 2. Now, these are 2 equations that are easy to solve. We get a solution set just like we did here. The logic here is that if a number of things multiplied together are 0, then any one of those things being 0 makes it 0. So we set each one of those things equal to 0. And the same thing here. Now here we really didn't need it because we can see that x equals negative 2 and x equals 4 are solutions. Here it's a little harder to see, so we write out the equations. Here. Now I changed this equation a little bit. I put a 3 in front of this just to make this as general as possible. So what I did was I divided both sides by 3 because if I've got the 3 out there, it's just not going to, what we're doing won't work. Okay. So what we then have is, well, both sides divided by 3, we end up with absolute value 2x minus 4 equals 2. If 3 times something equals 6, that something had better be 2. Okay. Again, that splits because, again, 2x minus 4 could be 2 to make this true. But if 2x minus 4 is negative 2, it's also going to be true because the absolute value of negative 2 is 2. Okay, so there it is. 3 cases, 3 of the problems where we have to split it into 2 equations. All right. Now, keep that. Okay, that's a good way to get it before. Here we go. Look at our problems. Not sure all that's visible, but everything we should work out. Okay, so we have the equation x over 3 plus 2 equals x over 6. We have denominators. In an equation. Multiply both sides by the common denominator. Okay, common denominator is 6. 3 goes into 6, and 6, of course, goes into 6. So we do 6. Now, people write it out like this, and a lot of people will write it out like this. In fact, most people write it out like this, but this isn't right. We haven't multiplied 6 by the left-hand side. We write it like this, we're just multiplying 6 by x over 2. We put parentheses in here and use the distributive law. So 6 has to multiply every term on the left side by the distributive law. If we not put the parentheses in there, we haven't multiplied the side by 6. We just multiplied one term by 6. Try to, need to understand that. Well, this can be written down as 6 times x over 2. And I write 6 over 1 by x over 2 because most people in this class really need to put that 1 there to remind themselves it's a fraction and what the roots of fractions are. And then you have 6 times 2. And that's going to be 6 over 1 times x over 6. Okay, well, now take the shortcut. That 2 will divide the 6, giving you 3. The 1's still in the denominator, but that doesn't make a difference. You just don't write it down. You get 3x plus 12 equals x. And the rest of it is very easy to solve. They want to solve it and check it, but that's all it takes. If you multiply both sides by 6, you eliminate the fractions. That's cause for great joy. Okay? If we eliminate the fractions, then the fractions can be tricky to deal with. Okay? So we don't want to deal with fractions. In an equation, we can always multiply by a common denominator. Preferably the least common denominator. But any common denominator will eliminate your fractions. If you use a common denominator that's too big, well, your numbers get a little bigger. You still get the right solution if you do. Okay. Now that really kind of brings us down to these last couple of equations. You've got x squared minus 2x minus 8 equals 0. This is not a linear equation. In review, what we talked about just in the last class or two. Not a linear equation, it's a quadratic equation. And you do quadratic equations much differently way you do linear equations. Now, there are two ways to solve the quadratic equation. Most of the quadratic equations that live out there in the wild, you're going to have to use the quadratic formula. I'm not going to spend a lot of time explaining this because it's pretty thoroughly explained just in our last class or the one before that. Okay. Quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Make sure you understand the explanation. And the reason I'm not going to explain it is there's a bunch of other stuff we've got to do. Okay, you have a very recent explanation. So go back and use it or read whatever. Here's the quadratic formula. A is a number in front of x squared, which is 1. B is a number in front of x, which is negative 2. C is a number that's left over, just a number without any x's on it. And that's negative 8. So x equals the negative of negative 2, because b is negative 2, and you got the negative of that, plus or minus the square root of b squared, which is negative 2 squared, minus 4ac. A is 1, c is negative 8. All that divided by 2 times a. And now it's just arithmetic. The negative of negative 2 is 2, plus or minus the square root of, well, square negative 2, you get 4. 4 times 1 times negative 8 is negative 32, and you got the negative of that, so that's plus 32 over 2 times 1. Well, no, we're doing the multiplication. That's just over 2 then. That's so much, make it as clear as possible. So there we have it. Okay, then this is 2 plus or minus the square root of 36 divided by 2. This equals then 2 plus or minus 6 over 2. So we have two solutions. Two plus 6 over 2, which is 8 over 2, which is 4. And 2 minus 6 over 2 equals negative 4 over 2, which equals negative 2. Solution set consists then of negative 2 observation. You could have also solved this by factoring. And of course, you need to know how to factor, which we've again done recently. Write out all your possibilities. Eliminate the ones that are clearly won't work, and then find the ones that will, if any. Okay, there's a test for that. But I'm not going to get into that now. Okay. Anyhow, you have this. So this splits into x minus 4 equals 0. or x plus 2 equals 0. With solutions x equals 4 or x equals -2. And these solutions agree with the solutions you get from the quadratic formula. The good thing though is that there's some equations that factor, but it's impossible to find the factors. Okay. You just never able to figure it out, either because factors are irrational or the numbers are just too confusing. But the quadratic equation will always work. It always gives you a solution. Okay, let's see. I think we can't use that. Okay. Now the last equation that I wrote out was x squared minus 2x plus 8 equals 0, which is just like the one we just did, except we have plus 8 rather than minus 8. That's going to make a difference. Let's see how that works. First, we identify as quadratic. So we use a quadratic formula. X equals negative of -2 plus or minus the square root of -2 squared minus 4 times 1 times 8. All that divided by 2 times 1, which then equals 2 plus or minus the square root of 4 minus 32. When we have a negative on the 8, we got a plus 32 here, which gave us 4 plus 32 or 36, and we have this, see what the square root of that is, but that's not going to happen here. It's going to be 4 minus 32. So this is going to be 2 plus or minus the square root of -28, all divided by 2, which is 2 plus or minus the square root of 28 times the square root of -1 over 2. This then is 2 plus or minus the square root of 28 times pi. Pi being the square root of -1 imaginary number. There are a couple of simplifications we can still make. We can divide both this and this by 2. But before we do that, we want to simplify the square root of 28. Is 4 times 7. Why do I do that? Because square root of 4 is 2. Since 28 contains a square, a perfect square as a factor, we factor that square out, so we take the square root. Then we get 2 plus or minus 2 square root of 7 times I, which is 2 over 2 plus or minus 2 square root of 7 I over 2. Well, the 2 divides the 2. It doesn't go away. A lot of people divide 2 by 2. Okay, that goes away because I cancel it all. That's another reason I don't like the cancellation. 2 divided by 2 is 1. 2 divided by 2 here is 1. And there we have it. Solution set is 1 plus the square root of 7 times I, 1 minus the square root of 7 times I. Now you might wonder why we do this. I've addressed that before. You know, but you got to go a lot further in mathematics to really understand why this is important. It first becomes really important with differential equations. We wouldn't have our technological society, uh, most likely, uh, without this convention. Okay, these are complex numbers. They're extremely important, perhaps even more important than real numbers. Okay, just take my word for it. And if you want a good explanation, at least, yeah, master your mathematics courses up through differential equations. However, most people are not on a track. Really, that wouldn't make any sense. It'd be a lot of work, very difficult, uh, and unless you're really curious, you probably have better things to do with your time. Uh, Although, if you are curious, I should advise you. All right. Okay, well, that's the equations. That's pretty much what you need to know to solve equations. There's more, there's rational equations and so forth. And yeah, maybe we better look at one of those. Okay, so let's try this equation. Darn it. So just a careless person handling the board, apparently. Looks. Okay. I'm going to slide back just to make sure everything was visible. And it appears that everything I did is blurred. Need a camera with fixed focus. I'm going to have to ask our corporate department to locate the one so we can order one. Let's try to focus. But let's just stop the recording until we get it. Okay, unfortunately, camera chose to blur everything out, and I don't know when. I know it was after we started this. So quickly, so we do this in just a few minutes. Got equation x over 3 plus 2 equals x over 6. If you saw this already, you don't have to see it again. Although if you enjoyed it, like again. The denominators, there are denominators in this equation. We multiply both sides by some common denominator, any common denominator, but the least common denominator is probably preferable. And that's going to clear out all our fractions, and then we're not going to have to deal with fractions. That's important. That's very handy. Okay, so we multiply through by 6, because 6 is a common denominator. 3 divides 6, and 6, of course, divides 6. We do 6, being careful to multiply 6 by the entire side, not just by the first thing we see. We multiply the whole side by 6 to keep the equation in balance, and then we multiply this side by 6. We put 6 over 1 here. Times x over 2. We do 6 over 1 because most people are not very adept with fractions at this stage. Some people are. But we can't assume that everybody's adept with fractions, so we do this so we keep the numerators and denominators straight. And 6 then multiplies the 2 by the distributive law. And again, we write 6 times x over 6 is 6 over 1 times x over 6 to keep things straight. Now, 2 divides 6 gives us 3, so we have 3x. 6 divides 6 gives us 1, so we just got a bunch of 1s. That leaves us x. Got 3x plus 12 equals x. There's still more to do, but that's straightforward. Okay, subtract x from both sides, and then subtract 12 from both sides, and then both sides by 2. Okay. Now we have x squared minus 2x minus 8, which is not a linear equation. A linear equation just has multiples of x and just plain old numerical terms. Okay, pluses and minuses of numbers. Okay. If you have x squareds in there and the rest of the equation is linear, it's a quadratic equation. We have to use the quadratic formula. Now, the equation has to be in the standard, in the general form, which is with everything on one side and zero on the other. And if you have an equation with squared terms and just plain old x terms and numbers scattered on both sides of the equation, you gotta do add and subtract on both sides until you got them all on one side. Then you can identify the coefficient of x, x squared, coefficient of x, and this number. And those will be your A, B, and C numbers. Coefficient of x is 1, coefficient of x squared is 1, coefficient of x is -2, and C is -8. Plug that into the quadratic formula, do the arithmetic. You get 2 plus or minus the square root of 36 over 2. The square root of 36 is 6. So we have 2 plus or minus 6 over 2, meaning our solutions are 2 plus 6 over 2, which was 4, and 2 minus 6 over 2, which simplifies to -2. Our solution set is a set 2, -2, 4, which turns out to be the solution set of one of our original equations. Okay. Now, we can observe that this equation can be factored. The left-hand side here can be factored. So if we know how to factor, we factor this into x minus 4 times x plus 2 equals 0, and do what we just did a little while ago. We get x minus 4 equals 0, or x plus 2 equals 0. Write that out so it reinforces x equals 4 then, or x equals -2. Our solution set is still -2, 4, same as it is. In the event of slightly different case, and yeah, okay. Let's see. Yeah, I think we see it all this. Let's just make sure. But we don't need to see. This is what we need to see. Okay. Sorry. I need a bigger monitor so I can see what I do. Small laptop, 10 feet away, so it's hard to read or the screen. Okay. X squared minus 2x plus 8 equals 0. Quadratic equation, use a quadratic formula, just as before. And we end up with a negative instead of that. Remember, we got a square root of 36. We do that. Square root of 36 is 6. Square root of -28 is a real number. There's no number you can multiply by itself to give you -28. So we write this then. Square root of -28 is 28 times the square root of -1. Now you can't do the square root of -1 either, but we give this a special name. We give this I for imaginary. This is your basic imaginary number. Imaginary numbers are imaginary, but they're not really necessarily imaginary. Turns out it seems like they're really needed at a fundamental level to do quantum mechanics, which pretty much allows us to read the whole universe. Okay, and a lot of important technology. So we can write this then as 2 plus or minus the square root of 28 times the square root of -1, but we write that as I. Then 28 contains a perfect square. 4 divides into 28. 4 times 7 is 28. So we split the square root of 28 into the square root of 4 times the square root of 7. And the square root of 4 is just 2. And we keep the I. So we just write this. Instead of 4, we write 2. And now we have everything so that we can divide both these terms by 2. 2 divides 2, you get 2 over 2. 2 divides 2, square root of 7i, you get 2 square root of 7i over 2. Well, then the 2 into the 2 gives you 1. The 2 into this 2 gives you 1. You just end up with 1 plus or minus the square root of 7i. Solution sets 1 plus the square root of 7i, 1 minus the square root of 7i. That's the third time I had to go through that. We wasted a lot of class time due to the technological glitch and then me forgetting to hit the button. Okay. Okay, just an example to refresh on some rules for exponents. We have this expression. So this expression simplified by raising every power to the third power, the power of every term. Okay, so we have x squared cubed, y to the negative 4 cubed, z to the negative 3 cubed. X squared cubed means x squared times x squared times x squared, which is x times x times x times x times x times x. Write that out, you got 6 x's. You have to understand that you're never going to keep rules for exponents straight. In any case, you think of that as you simplify this, and then you say, okay, that'll be x to the 6th. And now I know that I better multiply these exponents. Okay. So I multiply the exponents here. I get y to the negative 12. Multiply exponents here, I get c to the negative 9. Now, if I want to write this if the final form, you want a final form with no denominators, you write this as you can write the denominator as 1 over z to the 9th, because that's what a negative denominator means. Z to the negative 9th is 1 over z to the 9th. That's fundamental. You have to know that. You have to know all the rules for exponents and then be able to apply them. And that's going to be x to the 6th, y to the negative 12 times z to the 9th over 1, because when you divide by a fraction, you multiply by its reciprocal. So you end up with this form. Now, if you want the final form with no negative exponents, you're going to have x to the 6th, y to the negative 12th, over z to the negative 9th. Okay. Meaning what now? This means x to the 6th times 1 over y to the 12th divided by 1 over z to the negative 9th, which equals x to the 6th times 1 over y to the 12th times, that's not 1 over z to the negative 9th, 1 over z to the 9th, same as it was here. That's getting a little strange. Let me write it out. Linearly, play the board. Okay. That would be x to the 6th times 1 over y to the 12th times z to the 9th over 1. And that equals then x to the 6th, z to the 9th, over y to the 12th. Now you should ideally understand everything I just did. But if you don't, you can get away with this. If I've got a negative exponent in the denominator, I write that factor in the numerator, but with a positive exponent. If I go from the denominator to the numerator, my exponent will change sign. If I go from the numerator to the denominator, my exponent will change sign. So that this y to the negative 12th in the numerator became a y to the 12th in the denominator. A z to the negative 9th in the denominator became a z to the 9th in the numerator. And the same thing here. Okay, this was a z to the negative 9th in the denominator. By the rule for dividing by fractions, and a z to the 9th in the numerator. Okay, now this form has no denominators, but it's got a negative exponent. This form has no negative exponents, but it's got denominators. Okay, that's a fairly standard type of problem with exponents. Be a moderately challenging problem with exponents, but you've got to know exponents. Okay, so we're going to have to review a lot of stuff, and email me if you have questions on it. I'll have some office hours next week. I'll get those published. And you're welcome to come by and ask questions if you have. Okay, we could keep that picture there for a couple of minutes until the camera sees enough to stay focused. So, I'm going to just talk about electricity and magnetism, basic principles, right? And put on the Coulomb's law. Very straightforward. I'll write this way. I don't want to include this R with this one. I don't want to write an R cubed because it looks like an inverse cube law then. Don't want to write an R hat because people miss the hat, think it's the R vector. Okay, so writing it this way. Now, if you understand it in the other ways, okay. But remember, this is just a vector from one charge to the other, right? And it's a force of, well, charge one exerted on charge two. Okay. And we write it in this form. Now, if F12 means the charge on one exerted by two, everything is backwards. So I'm going to use a convention that F12 is a charge exerted from one on two. Okay. Now, you don't have to know where Gauss's law comes from. Okay. But it's just Coulomb's law for the divergence theory. That's Gauss's law. And that says you can construct a Gaussian surface on which usually you have a uniform, an electric field of uniform magnitude. Okay, with the electric field always normal to the surface. So I just say, our imaginary surface is always normal. And I should say imaginary closed surface. Height down here. This is Q enclosed, charge enclosed. Get your 4 pi K. You got your E times the area of the surface. Okay. In the notation I'll use in molecular calculus, you call that E times S, but that's the total area of the surface. And this is just an expression of divergence. So as you think about the divergence theorem, you'll understand the divergence theorem better if you understand it in this context. Okay. And you'll understand it here maybe better if you understand it multivariable. Multivariable is not required for this course. I just mentioned this because everybody's a multivariable. Okay. There's an important connection. Okay, that's Coulomb's law. The electric field okay, notation. If you have a charge distribution, any charge distribution, yeah, I'm sorry to talk about this. I'm talking about it. If you got volume, sample points, X star, Y star, Z star. Charge delta V is approximately this. Distribution to the field, X, Y, Z is KQ over R squared times R over R. Remember, test charge, one of these being the test charge, the force per unit of test charge, you just divide out the test charge, you get KQ1 over R squared. And then times your vector, okay? Now I'm being a little sloppy here because I just can't take the time to be rigorous. This is semi-rigorous. Your R vector is the x minus x star, y minus y star, z minus z star vector, the vector from your sample point to your field point. So if you add up all these things, you're going to do this over all possible volume increments. So this would end up as a triple integral over your region. Now we have a notation problem. I'm not sure what you're most used to. Notation problem is when you take the limit, your x stars and y stars and z stars become x's, y's, and z's, right? Okay. And we've already got x's, y's, and z's. So if we're going to distinguish the field point, we could, for right now, just put a little tilde over the x, y, and the z. And I could write that whole thing out, but I'm not going to take the time. You can write it out easily. Magnitude of this thing is x tilde minus x squared, r squared. Just be the square of this plus the square of this plus the square of this. Of course, you got an r here, so you'd have another square root of some of those squares. And the r vector would just be this, and the integral would come out the way it comes out. It's not going to ask you to do such an integral. That's in principle the way it works. Now, the ways we've seen the thing, okay, we haven't really done a lot of volume applications, but if you have a straight line, long straight line, and a point up here, call this point, I'm going to use the tilde notation just to help illustrate what we have here. Take a typical increment. I'm abbreviating a delta x with sample point x star. We have our r vector. And we set up the integral, do the integral. Now, I'm not going to do the integral. We just don't have time. We've got a lot of things to talk about. But this is something we've done. It's something your text does, something you need to know how to do. Okay. And your picture is kind of, if this is an infinite line charge, Then you have another R vector here, and you get two field vectors. And you can split the line in half at this point. And remember, these things kind of make a cone or a okay, anyhow, that's one situation where you've got to be able to show the integral. Another is you've got a disk down here from the XY plane. And if you've got charge density, lambda down here. Well, charge density lambda, sigma. On the disk. And you think of partitioning this disk on your distance from the origin. So your R would be here, R vector. Then you get the field from this ring, and then you integrate the field from the ring from the inside out, and you get a result for the field. Maybe at the center of the ring, but more likely the point up here. So I'm just telling you, you need to be able to do. These are two standard things you need to be able to integrate. So make sure you are up on how to do those integrals. I think we've done them in detail in class. Your text does them in detail. You can find them all over the internet in detail. It's very important. Cases. Then if the applications of Gauss's law to infinite line charge or cylinder. Okay, Gauss's law will give you the same result. This will. But Gauss's law is going to be particularly helpful here, as it's hard to come up with a surface because of the extent of the plane of the disk. You're not going to come up with a convenient surface that satisfies the conditions. Electric field always perpendicular and always uniform. Okay, so you got to be able to use Gauss's law. Okay. That allows you to do electric. Now there's more to it, but these just kind of the hypotheses. Okay. Potential difference. Constant D. It's just D times delta S. to write this? Is the integral from A to B of B dot ds? No, they're not a good place to do it. I'm gonna squeeze it in here. Can't read that. I said E, electric field's conservative. Okay, now how can you tell electric field's conservative? Again, just invoking stuff that should be near and dear to your heart from multivariable calculus. Its curl is 0. It's one test for conservative field. You don't have to know that for this class, but it's something that I think you do know that's going to be helpful to you. Okay. So the curl of E is 0. It's path independent. That means it's conservative. I mean, it's path independent. It's the gradient of some other field. It's a gradient of your potential field. Okay, potential function. Okay. So that's important. But one application of that is to a capacitor. So on a capacitor, remember you got capacitor plates. You have charge. Density sigma. You're going to have an electric field. Going to be a constant electric field. So it should be able to use Gauss's law to figure out what the electric field is. It'll be 4 pi k sigma. Okay. I'm not going to write it down. It's something you really need just and be able to derive. Just put a Gaussian surface around the single plate. The flux penetrates both sides of the plate. Just put a Gaussian surface around this plate. Flux penetrates here and here. Flux is 4 pi k cubed. And half of it on this side, half of it on that side. This plate the same, so it ends up being again 2 pi k cubed from each plate. You get 4 pi k cubed. I'm not going to write that down, just take too long. But there are the words. Okay, the charge density sigma. If this separation is A, and I think that's a fairly commonly used term, your potential difference is E times A. It's a word per unit charge. Plate to plate. Now, there'd be a little correct. I'll put absolute value signs around this. Okay. Potential difference is positive in one direction, negative in the other, right? Okay. Potential difference is equal opposite to the work done by the conservative force on a positive charge. So you can work out those differences. Okay. We'll work out those details. I'm talking about capacitors. You want to charge a capacitor. And, yeah, capacitance is the amount of charge you have per unit of potential difference. Here's your potential difference. Your electric field is determined by your charge density, which determines, along with the area, the electric field. And it all interrelates in a way you want to try to pull together. Okay. Now, if you got a capacitor in the circuit, initially uncharged, closed switch, the thing charged. The charge on the capacitor is Q. The voltage equals QC. This implies in a way that you want to try to connect okay? If you think about what it takes to move the next increment of charge, the work is going to be QB, which is QC. So you move a charge delta Q. Okay, to move the next delta Q, you're going to multiply delta Q by V to get the work required, the energy required, which means you're going to multiply QC times delta Q, which means that the increment of work is QC times delta Q. And I said delta theta, it's delta Q, it's DQ. Put the line in the wrong place there. Okay. There's your energy. And then you also have energy per unit of volume. You take the volume between the plates, get the energy per unit volume. Okay, those are important ideas, important concepts. And that leads you to a general expression for the energy in an electric field, the energy density in an electric field. So worth your attention. Yeah, we might come back and talk a little bit more about the electrostatics, but let's talk about conduction. J is current per unit area. Pure surface perpendicular to J. Incidentally, put that together with Stokes' theorem. And you find magnetic field, the average magnetic field around the boundary of that region. But nothing about that. Okay. Okay, so J's current per unit area pure surface perpendicular to J. Say it this way, J is proportional E. Proportionality constant being the conductivity, which is reciprocal of resistivity. And now, if we've got a chunk of wire here with constant electric field, where A sub CS means cross-sectional area, got constant cross-sectional area, constant electric field, then A equals when you use a symbol for conductivity, that's fine. I'm going to write it out because sometimes it's hard to remember what symbols mean. J is conductivity times electric field. Current is then just your current density times your cross-sectional area. Very simple idea once you get it through your head. If your wire length is L, then the potential difference is B times L. Okay. You think about units, if you wish. Okay. If voltage is what? Number of joules per coulomb. Okay. E is your number of newtons per coulomb. So E times L is your number of joules per coulomb. Multi-newtons by the meters of your length, you're going to get joules. Okay. And you can look at the introductory problem sets. It might be good to scan them because a lot of this stuff is addressed intuitively. I mean, you want to develop intuition. Got plenty of other stuff you could be looking at. If the bar has length L, the potential difference is G times L equals G. Current is J times the cross section. So greater V implies greater E implies greater I. I don't want to take the time to do all the actions. Resistivity is rho equals, oh, sorry. Write things down without thinking. Actually, I wrote it down, right? Okay. Resistance is rho L over A, where rho is resistivity, which is just simple conductivity. Conductivity is related up here. And you put all this together, and you have a Ohm's law. I, which is equal to J times your cross-sectional area. Remember, cross-sectional areas related down here. All these relationships go together, give you Ohm's law. Current equals V over R. In a circuit, power equals work divided by time equals current times voltage. Just to note, current is joules per second times highest coulombs per second. G is joules per coulomb, which is joules per second. That reasoning. keep this straight. Um, Other things in circuits is, well, yeah, resistance in series, resistance in parallel. Also, capacitance in series and parallel. Okay, relationships have exactly the same form, except what you get. The relationship for parallel here is a relationship for series here. Relationship for series here is, sorry, for parallel here is the relationship for series here. We talked about this, about combinations of capacitors and stuff. I don't have time to go over that, or combinations of resistors. But go back and see why these laws apply. You got resistors in series. It comes out because your voltage drops are the sums of the voltage drops across. The total voltage drop is a sum of the voltage drops across the resistors. A couple other things about basic circuits. Um, because of this, the voltage drop is current times resistance. Those are kind of your main tools in dealing with just fundamental circuits, other than circuits involving capacitors and inductors and stuff like that. And we'll just deal with those circuits within the concept of an LRC circuit, as we talked about last time, and we'll be playing around in lab, okay? And I'll talk about that at the end here. Give you a little perspective on it. I haven't addressed dielectrics and stuff, because that's pretty simple. Put a dielectric between the plates of the capacitor, you enhance the electric field by separating charge within the dielectric. And if the dielectric constant is 80, you get 80 times the field, so you get 80 times the capacitance. And such things. These are kind of general principles that I want to focus on right now. Okay. You really want to understand the things I'm talking about. It makes it easier to understand everything else and see how things tie together. Okay, now the beginning of understanding magnetism is QVB. Now, QVB by itself is of limited use. QVB is just kind of abbreviation for the fact that if you have charge Q moving with velocity V in a magnetic field, force equals QV cross B. If you have a current running through anything, and there's a magnetic field. Force equals IL cross B. One put a K prime in there because that picture just evokes the next thing I'm going to talk about. So I'm going to get ahead of myself. Now, there are implications of this. You've had problems where you got two parallel wires. Okay. If you've got a wire in this direction, but with current flowing in this direction, you're going to have a magnetic field around it like this. That magnetic field impacts the current here, and if this current's in this direction, magnetic fields like this, currents like this, and this conductor is going to be experiencing a force in this direction. If currents are in opposite directions, then they'll be attracted. Okay, and you can work that out just from these things, just by applying these principles. You want to know these things. You want to prepare to think through these things. Okay. If you've got a charge moving in a magnetic field, charged particle in a vacuum, in the absence of any significant gravitational attraction or gravitational force, then as we've demonstrated, and I wave my hands over it, if you're moving around a circle, if you're moving in this direction with a magnetic field upward, positive charge, QV is here, V is here, going to experience force in this direction, which will not influence its speed because the force is perpendicular to the motion, but it will influence the direction. So it'll turn a little bit, and now it's turned, magnetic field is still here. You do your QV cross V, and you get the force in this direction, always perpendicular. That's going to cause circular motion. If you know the mass of the particle, strikes the magnetic field and the charge of the particle, you figure out the radius of curvature. And that came in very handy in determining the mass of an electron. Okay, determine the charge of an electron by how quickly charged oil drops falls in an electric field. Okay, a little bit complicated because you don't know how many charges there are, but you can get a bunch of discrete values and you make the conclusion to figure out what the charge of an electron is. Then you put an electron beam in a magnetic field, you accelerate the electrons through a given voltage, put them into the magnetic field, measure the radius of curvature, and conclude what the mass of the electron is. Very neat stuff. And I'm sure you've read about it. Okay. Worth reading about, worth thinking about. It's another good example. It's historic, it's really important. And it's not too hard to understand. I kind of recommend trying to understand that. Nonsense experiment. Okay. Got this, we got this. The other thing about magnetism is delta B equals K prime times the distant I delta L cross R over R squared. This is R over R cross product. And that would be the contribution to the magnetic field if you have, again, the same picture I have here, current flowing through a wire. They point out here, and you got an increment delta L here. And I delta L is a vector in the direction of You multiply I by delta I, so much current flow in here. You got a field point out here. Here's your R vector. Uh, you integrate that, you get the field of a wire. Okay, a long wire or a short wire because you can do a finite interval. Okay, that's the important one. I'll emphasize that. You also could replace your I delta L by a QV. Okay, K prime times QV cross R over R squared. With the R vector divided by R as well. That gets really interesting because you've got a moving charge. The magnetic field at this point is going to change as the charge moves. And if you have accelerating charges, you get electromagnetic radiation that we didn't get a chance to talk about. So kind of neat stuff. You should be well prepared to understand that, though, if you understand this much about the magnetic fields. Now, let me just be sure that I'm not leaving something out here. Okay, so there's a formula for the magnetic field surrounding a wire. You should be able to derive that formula using an integral. You ought to be able to integrate these I delta L over R squared cross R over R things because we did it in class. But at the very least, you need to know what those formulas are. Okay. Now, an easy formula for a magnetic field is you have a loop of current of radius A. And I'm drawing this kind of small because you've done it a number of times. And you've got a delta L up here. So that your I delta L vector is perpendicular to the R vector. What's the R vector? The R vector is from your sample point in the increment. I really should draw that bigger. From your sample point in the increment to the center. Since I'm going to draw that, I better make it big enough so you can see it. Okay, so you've got a loop. Badly drawn loop. We've drawn this and gone over it in detail. You got radius A, and you've got some delta L here, you've got current I. Then your R vector is I delta L, produces field. I do know that. So you're taking to keep writing it down. Um, Cross product. Some of your delta B's sum your K prime I delta L over R squared R cross R over R. But your delta L cross R is always, in this case, going to be upward. Wherever you are, your I delta L is perpendicular to R. So what you end up with is a sum of K prime I delta L over R squared and of course, the magnitude of your R vector is just your radius, which is A. This point, I'll replace R squared by A squared. R over R, this vector is a unit vector. It's perpendicular to delta L, so the magnitude of the cross product is just delta L. Okay, so you've got I delta L over A squared, and you pull out all the constants, which are K prime I and A squared. Have to sum your delta L. You let your increments go to 0. You get K prime I over A squared times 2A I, which is 2 prime K prime I over A squared. Okay. And you can express that in terms of mu naught. And it's not over A squared, it's over A, because of course this A is A provided you just see A in the denominator. Now, that's an argument that you absolutely ought to be able to give. I ought to be able to ask you to show me what the field is at the center of that disk or center of that circular loop, and show me why. Not sure if that's going to be on the test. There's going to be some randomization when I finally generate the thing, but that and things like the electric field of a circular disk or the electric field of a loop of, of a ring of current of charge. Okay. Then you can extend this and you go back. I'm not going to do it here. You can ask yourself, okay, what's a field at a point? At Z, if this is the origin, it's some given Z coordinate or some height above the center of the loop, but on the axis. This is really important for understanding what we're going to do in lab problem. This is where your magnetic field comes from. It comes from currents in the loop. Okay. Okay. Now, if you then start changing the magnetic field within the loop, okay, current loop produces magnetic field. Inside and around the loop, dissipating as you get further and further into the loop. general. Because again, to evaluate the integral, you have to use multivariable calculus. Be sure you relate this to what you're trying to pull together in multivariable calculus as well. Okay. Magnetic field inside the loop results in the flux through the loop. Remember, your magnetic field of that loop is going to be perpendicular to the loop, you know, inside the loop. It won't be constant. We can only calculate it exactly. I'm maybe stretching a little bit, but I think you'd have to use approximations any place but at the center. But you got a bunch of loops wound into a solenoid. You get a pretty constant field inside, and Ampere's law shows you why. And we'll talk about that today. Magnetic field inside a loop results in a flux through the loop. If the current changes, flux changes. Producing potential difference negative d phi b dt around the loop. That's basic principle that if you have a changing magnetic flux within a region, that you produce an electric field around that region. It's the way light propagates. You got these electromagnetic fields that want, keep oscillating. And unfortunately, we haven't been able to really talk about that. Okay. But if you understand these principles, you're ready to understand propagation of light, electromagnetic radiation, and so forth, which might well become important, especially if you're in certain areas of electrical engineering. For mechanical engineering, maybe you're building waveguides, and you still have to understand the way the fields work. Anyhow, that's a side comment. This is generally true. First thing you see in the introductory problem sets, we talk about induced currents, induced voltage. Okay. This is, of course, self-induction. Magnet spinning in a coil also changes. Flux. Changing the voltage by changing the flux. Rate of change. B minus. Okay. We're going to get our hands on that tomorrow, so you should understand that pretty well. Um, not going to be able to talk about everything. I got 10 minutes left. I'm going to give you a picture of the LRC circuit, LI, LR, LR, LC, and RC. Okay. And I'm not going to do any introduction to this, except for just sketch. And here's your conductor. Here's the resistor. Here's the capacitor. Full voltage drop. This is just you got a current on. I listed these yesterday, voltage drops. Voltage drop here is, well, the voltage change across your inductor is L d I dt. Change across the capacitor is Q over C. Change in voltage. Change across the resistor is I times R. From that, conservation of energy and so forth tells us that L d I dt plus Ri plus Q over C. In this case, equals 0. And I said it's too bad we don't have another week where we could have some driving voltage out there and alternating current and so forth. Okay. You might read the note. It's a fairly extensive note I put in the video from last time, just a written note. Might be worth looking at. I thought it was worth looking at when I wrote it. Okay. Look at it again, I might think, oh my gosh, what did I just do? But usually I do take another look, and usually right, it's either worth keeping up there or worth having been modified. Okay, well, anyhow, okay, you got this. Okay, that's simple. Okay, what happens? Let's say you got a lot of charge on the capacitor at this instant, okay? And not much current flows through the inductor. Well, you got charge and capacity, you got some current, you got some current in the inductor. Let's say that you're reducing the charge on the capacitor in it, okay? Well, as this reduces, not, I'm going to get it that way as an explanation. Okay. All I'm going to say is, if you have the capacitor and inductor in series without a resistor, you get an oscillating circuit, oscillating current. The capacitor has a charge which is going to discharge through the inductor, okay, which builds a charge in the inductor, but the inductor resists the building of that charge. So eventually the inductor has a lot of current. The inductor reduces the building of current by this, okay, back EMF. But eventually it gets its maximum current when the capacitor is discharged. As soon as the capacitor is discharged, there's current here. The inductor starts discharging. Current in the inductor starts decreasing, which then recharges the capacitor. Okay. And that just continues. Now you can do the equations and stuff like that, and I'll give you more detailed explanation. I have more than 5 minutes left, but we've already talked about this. Okay. Now, without the resistor, remember, the power is IR. You're losing energy here. This thing's heating up. You're losing energy. Now, if it's just a little resistor, then you're not losing too much power. Okay, if it's a big resistor, you're losing a lot of power. With no resistor, you have the LC circuit. Okay, and as we've seen, your voltage drops are LDI dt and Q over C, but I is just dq dt, so this is L Q double prime plus Q over C equals 0, Q double prime equals negative Q over LC. And you remember we talked about this last time we did that solution. We did the solution for this one. And if you look at the video, just as soon as you left, I took a look at the book. I said, okay, thing has to be in this form. And I was one step from having it in that form. I factored out that R over L, and then I just couldn't get the thing into a form that made obvious sense. Okay. Point is, you get this so that Q equals some Q max times the cosine omega t plus phi. Just totally analogous to what we did with a simple harmonic oscillator with a constant restoring force, with a restoring force constant. So this is like your restoring force constant here, Q over C, well, Q over LC. 1 over LC is your restoring force constant. Q is like your position. Just like X double prime equals negative KX, which leads to the oscillatory solution, except it's not a Q anymore, it's an X. Hopefully you remember that. Hopefully you review that, make sure you understand that you have a differential equation course. It's very basic, very fundamental. If you toss a resistor in, then you've got this. If it's just a little resistor, it'll still oscillate, but it's losing current. So you get these oscillations that gradually decrease. Okay. If you leave this out, then you just have an RC current. I'll do it real quickly. Okay. And you have this if there's no voltage source in here, which means you got Q prime R plus Q over C equals 0. So that Q prime equals negative Q over RC. And we did this yesterday, or last class, Monday. And you get this decreasing exponential. Okay. So that's this thing. If you leave the inductor out, you're going to get a decreasing exponential. Just the capacitor is going to discharge through this. We've observed it. We've seen the curve. You know what that curve looks like. If we took up the apparatus, we looked at the curve even with that semi-functional apparatus we were using at the time. Remember doing that? Should be a stark information. And then, of course, we could leave out the capacitor, and you end up with, again, like an Li prime plus Ri equals 0. Well, okay, quickly. Leave out the capacitor. You have Lr. Differential equation has exactly the same form. L I prime plus Ri equals 0. I prime equals negative R over L times I. And it's going to be exponential. Okay. Wish we had more time and wish I was a little smoother in what I'm saying here today. But so be it. That's a sketchy overview of stuff you're going to need to know. Okay. If you want to fill in some of the blanks, feel free to ask questions. I'll be here for office hours, mostly Monday, Tuesday, and Wednesday, probably around 12 to 2, plus a little bit one end or the other. And want to go over anything we can do. Of course, tomorrow we'll have a lab and we'll sketch in more of this stuff. Okay.